Hello friends, welcome to this video, and in this video we are going to learn about UNET-R, that is UNET transformer. We are going to implement it in the TensorFlow framework for 2D image segmentation. So before moving on to the next part of the video, make sure that you subscribe the channel and hit that bell icon. Now let's get started. Our first question is, what is UNET-R? It's a 3D medical image segmentation architecture that uses a transformer encoder and a CNN based decoder to predict the segmentation. Now, what are the key features of UNET-R? It uses vision transformer as encoder to learn global contextual representation. Second, it uses a CNN decoder to upsample the global representation and generate the final segmentation mask. So these are the two main features of it. So you can say UNET-R is equals to VIT plus CNN decoder in simple terms. Now this is the block diagram of the UNET-R taken from the original paper. Here you can see the depth, which refers to 3D segmentation, but we are going to utilize this for 2D. So make sure when we work on the implementation, you ignore this depth part from it, because in 2D segmentation we do not have depth, we just have height by width then number of channels. So we'll take advantage of this while implementation. Let's move to the next part. So next is, what is vision transformer? As vision transformer is an essential part of this UNET-R, so we'll study a bit about it. So we can say vision transformer is an architecture that is used for image recognition. It is based on the transformer architecture that was originally developed for natural language processing. VITs have been shown to achieve state-of-the-art results on a variety of image recognition tasks, including ImageNet classification. So one of the essential thing about VIT is that it takes your whole image, then convert it into patches and then feed those patches to the transformer. Now the conversion of whole image into the patches is also a task. So we'll learn about it in the slides next. So for the UNET-R, we are going to use the VIT base as it is used in the original paper. It uses 12 layer, 768 hidden dimension, and MLP size is 3072. Number of heads are 12. You can use VIT large or VIT huge, it's up to you. But for this video, we'll utilize base 12, and these are the configuration of this VIT base. Now we comes to the one of the essential part working when you work with transformer for computer vision, how to transform the image to patch. So you can see we have this input image. Now we need to transform it into patches. Here you can see individual patches, and if you little zoom it, or you can maybe you can see each patch is having its own name. So this is the size of our original image, and we have converted it to a patch size of 32 by 32, and according to calculation we have 256 number of patches. So how do we transform this? How do we do this processing? So let's study about it. So here's a simple example where on the left side I have written the theory, basically means the formulas, and on the right side we have example. Okay, so first we have our input image, that is H by W by C. So in example we have an input image of by 200 by 200 and 3 as the number of channels. Then we have our patch size. So we initially decide what would be the patch size. So for this example, we have a patch size of 25 by 25, that is the patch height and patch width. Now the formula for number of patches, that is n, is equals to height multiplied by width, that is image height multiplied by image width divided by patch height multiplied by patch width. And here we'll do the same operation, 200 multiplied by 200 divided by 25 into 25. So in total the calculation comes to be 64. Now what I want you to pause the video and check if my calculation is right or not. and if it is not right, comment below. Okay, I know it's right, I'm just saying you to do the calculation, just that. Now we have this number of patches. Now what is the transform input which we gonna give to the transformer? So it would be represented as n, that is number of patches, comma, then we have patch height multiply by patch width, then number of channel. So in that case, transform input would be like 64 by 25 by 25 by number of channels, and in total it became 256 by 1875. So this is one of the simple thing, but it is tricky if you don't know about it. It can be confusing at time. Even initially I was also confused with it, but once I understood it, it's really easy to work with transformers. So now we'll move on to the implementation part of it. So let's open our editor, and here we are. So first of all, what we do, we're gonna import all the layers. First we have imported the TensorFlow, then we have imported TensorFlow layers as L. So from there we'll call all the layers. Then in the line third we have imported this model class, which will help us to build our architecture. So let's start with the MLP part of the transformer. Okay, so we'll implement some blocks and then we'll implement our main UNET architecture. Okay, so we'll say MLP. Okay, it's going to take X as the input, and CF is a configuration file basically. So this configuration file is basically a dictionary inside which we'll define all our hyperparameters. So for now, let's continue, and after MLP, I'll show you the complete dictionary with all the hyperparameters. So let's say L dot dense. Then it requires number of units or number of features. So we have MLP dimension in the dictionary. We'll add it, and inside the transformer encoder, we'll have the GLU as the activation function, as this MLP would be uses inside the transformer encoder. So we say activation equals to GLU or GLU. Then we have dropout. So dropout rate would be dropout rate. Inside the dictionary we'll define them, don't worry about it. Okay, so this is done. Now we have another dense layer and one more dropout layer. Okay, so this is our MLP, multi-layer perceptron. Now before moving, let's just define the dictionary first. I think I need to define the dictionary first and then begin with the module, but don't worry, it's all the same. So let's have our configuration dictionary. So this is config empty dictionary. Then we define all the parameters, the hyperparameter which will be utilized. Okay, so we have an image size of 256 by 256. As both height and width are same, in our case I'm assuming that is why I have just written image size. In your case, if both height and width are different, so you can say image height and image width separately. Then now number of layers 12, hidden dimension we have written, MLP dimension which we have utilized now. Then we have number of heads, dropout rate which we have used here. Then number of patches, we have already calculated them. You can also calculate using the formula which you have defined in the previous slide. And next we have patch size. So now you have both image size and the patch size. I think you can do it. It would be 256 square divided by 16 square. Then number of channels. So this is the whole configuration file. Now whenever I say CF and do this, so I hope you will understand what this means. Okay, so we are done with the MLP part. Now we'll do the transformer encoder part. So before that, let me just give you an overview about the transformer encoder. So this is the transformer encoder. So it begin with the layer normalization. Then we have multi-head attention, and then we have this skip connection we added here, or you can say the residual connection we have. Then the added result would be followed by the layer normalization. Then we have MLP, which we have implemented just now, which uses GLU activation function. And again we have the residual uh, connection, and this encoder block is repeated 12 times because the number of layers here are 12 because we are using PIT base. Now let's move back to our editor. So let's implement the transformer encoder. We have our input as X and CF the configuration. Okay, so let's say skip 1. Okay, skip 1 equals to X. Let's move back to slide. Here you see the input is acting as the first residual connection or the skip connection. Okay, so that is why I've saved its value in skip 1. Then it is followed by the layer normalization. This is done. Then it follows a multi-head attention. So TensorFlow provide you the implementation of multi-head attention. So I'm using that only because that is more appropriate and easy for you. Okay. So if you want another explanation video on this multi-head attention, just comment it down. I'll make another video on its implementation along with explanation. Okay. So it takes the number of head that is defined in the dictionary and the key dimension. So one fact about this transformer is that the input dimension, the number of features as the input, and after the number of transformer layer complete remains the same. That is hidden size or hidden dimension. This hidden dimension what we refer. Okay, so this multi-head attention is done. Now what we need to do, we need to add both the output of multi-head attention and the skip one. Okay, now this output X would act as skip 2. So we save it. Now again we have a layer normalization followed by the MLP. So we are done with that. Now again we have skip connection. We're going to add or residual block, you can say. I think a residual block term would be more appropriate because it's really short. Skip connection are usually large, skipping a lot of layers and then connecting, especially in the segmentation. We call this from skip when we take features from encoder and concatenate or join them at the decoder. So we are done with the transformer encoder part. It's really easy to implement. Just layer normalization, multi-head attention, we have a residual block, then layer normalization, MLP, again we have a residual block, and we are done. Also, if you remember, we have the convolution decoder. So we'll define some convolution layer also. Okay, so our first function would be called conv block, and it take X as the input, the number of filters and a kernel size, and this is the default value. So first it has the convolution layer followed by the batch normalization and ReLU activation function. Okay, now here you will see, like, this is one of my question also. In the transformer architecture, they have used layer normalization. In CNN part, they have used batch normalization, and the activation function in the transformer part is GLU, and in the CNN part is ReLU. I haven't done much research on this fact, because initially the VIT, they use this layer normalization and the GLU. So I think author have directly followed them, and for CNN these are the most commonly used. So maybe any one of you, if you know the answer, please comment it down so that rest of us can also know. Or in my upcoming time, I'll write a blog post on it, this UNETR. In there I'll do some more study, and then answer this question. So this is the kind of homework for you all. You can try to find the answer to this question. Even just try to use ChatGPT or Brad, maybe that can help. Okay, so we are done with the conv block. Now we'll have another function called decon block. Basically here we have a transpose convolution. So this decon function take input, that is x the tensor, then number of filters. So we take this layer con 2D transpose. So what it does, it basically increases the height and width of the feature map. Basically it upsamples. Upsample don't here refers to bilinear upsampling. That is one of the technique of increasing. But here the this con 2D transpose, it learns how to increase. Okay. So these are the number of filters, a kernel size of 2 by 2, padding same, and stride 2. So here strides 2 refers to upsample the feature map by factor of 2. So if your feature map, that is x here, its size is, let's say, is 64 by 64, then when we give it as the input to this con 2D transpose layer, and we have this output, so this output height and width would be 128 by 120, that is double of 64 by 64. Okay, so we are done with the function part. Now we'll move on to the UNETR. Build UNETR 2D. Just remember that is a 2D implementation of it. So first of all, we have our inputs, input layer. First we have the input shape. So I hope you all remember the input shape. So let me write it down. So first we have number of patches. Then we have patch size, that is patch height multiplied by patch width, the number of channel. Here both patch height and width are same, so we refer to them as patch size. Patch size multiplied by patch size. Let me copy it here. Then number of channels. Okay, so this is done. Now we're gonna define our inputs layer, and we're gonna give patch, not patch, the input shape as the input. Now let's print the shape of this layer. Okay, so we'll call our build UNETR function here, give it the configuration file, not the file, the dictionary. Let me run the, okay, so you can see it's none 256 by 768. So let's write it here for our reference so that we know. Okay, so we have patches. Now we need to convert them to this patch embeddings. So this patch embedding, basically first it is followed by a dense layer. Okay, so we're going to say patch embed. So first it is followed by a dense layer. So now the what would be the output number of feature in this dense layer would be hidden dimension, and this would remains same through the entire transformer encoder. Okay, and this does not take any this what activation function. Okay, so we have given this as the input. Okay, now let's print it also, just to check its shape. Like while implementation, the shape is really important. Okay, so it's same as the above. Let's just do one thing. Let's try to change the patch size. Let's say this is 32. Let's run this model now and see. Okay, I have removed the shape. Let me comment so that we can compare whether this change or not. Okay, this is just to check it. Okay, again 760. Okay, the hidden dimension would be same. Okay, let's also print the inputs along with it. That is my mistake. Hidden dimension we haven't changed, and I'm trying to see the effect. Okay, see, this time they both are not same. This is what I'm trying to show you, that This 768 and this 768, this is just a mere coincidence. Maybe if you get confused, so if you change the patch size, so this value would change, this would remain the same as I've shown you. Okay, just I hope you have got it why they are same. Okay? Now we are done with patch embedding. Now what we're gonna do, we're gonna add the positional embedding in them. Okay, now why positional embedding? So let's move back to our slide a bit. Okay, so you see what here we have done, we have transformed this image into patches. Now each patches have a specific sequence, what come after what come before, you cannot randomly give. Okay, so to make sure that the model learns to have a sequence, okay, to give the sequential information about the sequence of these patches, we add a positional embedding, that is this 1 2 3 kind of this information. Okay, just ignore this part, we won't use this extra class embedding with our PIT implementation for now. Okay, because this is usually used for classification, but here we are dealing with segmentation, so we don't need this extra learnable embedding. Let's move back. Okay, so we'll have positional embedding. So first of all, what we do, we'll have a sequence. Okay, we have a range of numbers, so this is that we have the position, that is from tf dot range start 0 till number of patches, and delta basically the difference between 1 2 3. Okay, so let me print it and we're gonna see. Okay, here you can see the sequence 0 1 2 3. So it's basically the sequencing for our positions, the number of patches we have. Okay, so its shape is like 256. Okay, now we need position embedding, and here we will use the embedding layer input dimension. For this would be number of patches. Okay, and output, that dimension would be same as this hidden. Okay, so now let's print its shape also. I hope like you are understanding how we are going. Okay, if you have any question, just make sure you comment it. Okay, what I've done, I have done a simple mistake here. I haven't given any input to this layer. This is why it is having this error. Okay, so this is the shape. Okay, so we are done with this position embedding. So what we're gonna do, we're gonna take this patch embedding and add positional embedding in it. So this is our now feature which will pass via the transformer encoder. Now before moving on to the transformer encoder, let's just get back to the block diagram. Okay, here you see we have this Z third, Z6, 9 and 12. These are important because they are going to be used as skip connection in the decoder. Okay, so we need to save the output of these layers. So Z third means the third encoder layer, 6th encoder layer, 9th encoder layer, 12th encoder layer. So this is how it. Let's go with that. And while working on the encoder, we need to remember that we need to save these output of these layers. So we have transformer encoder. Okay, so I'll directly copy paste some variables. So this is skip connection index, third, 6, 9, 12. Then this is the skip connection where we would save them. So we'll say for I in range. Okay, just remember these are the layer number, third layer. Okay, and if we write range, it would, so we will say from 1, begin with 1, because by default it would begin with 0, so it would say 0 1 2. So basically if it begin with 2, then 2 would be the third layer, because 2 is the index number. So we'll begin with 1. Okay, then configuration, number of layers plus 1 and 1. So this is the starting value, ending value, and how much increment. So we're gonna say, so x is our input. We're gonna use our transformer encoder function here, configuration file, and now this is the output. So we would check if this I is appearing in this. So we would say if I in skip connection index, if it is, then skip connections dot, no, it's mistake, it's append. So this is done. Now we are done with this transformer encoder part. Let's for now just print the shape of it and see if it's working fine till now or we have any error. Okay, so till now we are fine, we don't have any error. Now we are moving on to the CNN decoder part, and this is a bit tricky. It would take some time to implement. CNN part is really simple, just a for loop and things are done, but we don't have same thing for the CNN decoder. So first of all, let's extract our skip connection from this list. These are Z third, Z6, Z9 and Z12 from skip connections. Now let's move back to a slide. So now if you see, we have these skip connection. Okay, Z third, 6, 9 and 12. And if you see here, the author in this paper is reshaping them to height, width, depth and the number of filter. So we need to ignore this depth part first, and we also need to reshape them to height, width and number of channels. So let's do that first. Okay, so we'll say first Z third would be L dot reshaping layer we have here. So now you may ask, so height over 16. So 16 height is basically input image height, that is 256 in our case, and 16 refers to the patch size. So 256 if you divide by 16 in our case, okay, in our example 256 is the this image size, that is height, and this 16 is the patch size. So if you divide 256 by 16, it would become 16, that is the patch size. Okay, so that's what we can simply say, let's me calculate it here. So we can say height is equals to cf dot image size divided by cf dot patch size. Okay, so we have height, same we have for width, so we're gonna say as s size. Okay, so we're gonna reshape them size by size, then hidden dimension 768. So that is like z third dot shape 0, not 0, should be -1, because this is the shape and we want last one. Either this one way or another way is, because we know it is hidden dimension this way, and input z third. So for now let's print it. Okay, see if it is working or not. Okay, you can see 16 by 16 by 768. If your height is different, height or width of them is different, it would be different. Let's do it here. Let's say our image size is, let's say 512. Now a double, so instead of 16 I think it should be 32. Okay, we have an error I think, because we also need to make modification above. Okay, something here we need to, I think it's better we do not reshape. let's stick to 256. Okay, so we ultimately we have got it in a proper manner. Height, width by number of channels is fine with us. So we're gonna copy this. So we're gonna say 6, then 9, and then 12, because all of them would be of same height and width. Let me print their shape just to confirm. Let us confirm their shapes if we are going in the right direction. So 16 by 16 by, so things are fine here if you see. So let's move to the next part. Okay, if you see, we have these 4 layers also, and one from the input. So input also is in the form of patches. So let's also convert it into height by width by number of channels. Let's do that part also. So we're gonna call it Z0 for now, and dot reshape, and it would be CF image size, CF image size, then CF number of channels. So let's print Z0 here. Z0 refers to input, original input. Okay, again see, mistake, I haven't given any input. These are common mistake. Actually I work with both PyTorch and this, so I kind of got confused sometimes. You can see original input shape 256 by 256 by number of channels we have. So this reshaping part is done. Reshaping part is done. Now we'll begin with Z12. Okay, and if you see this, just match the blocks here and see what they're doing. So this first Z12 would be followed by deconv, and if you here you can see this is the input size 768 and output is 512. Okay. Here you can see the sequence they follow. Just see 512, 256, 128, 64. Usually it decreases by a factor of 2, and same if you see it follows the same thing. So we'll stick to this it's this way: 512, 256, 128, 64, this thing. So let's begin. So what we need to do first, a deconv, and this, then this deconv plus this conv block. So first let's do this part, Z12. So let's say this is the decoder one. So what we need to do, we need to take X, the previous. Okay, no, okay, sorry, this X is the output of the deconv block. So its input would be Z12 and number of filters would be 512. So we are done with this part. Now we need to work on this Z9. So this is a skip connection. So this blue box, deconv, and then a conv block. Simple. So let's call it S as its output. So you're gonna say deconv again. This time input would be Z9, again 512. Then next it is followed by the conv block. Input S, number of filter 512. Now back to slide. Now we need to concatenate it. So for concatenation, we need to make sure that they both have same height and width. Let me run the program and check. Okay, so they both have same height and width, even the number of channels are same, so they would work fine. So we're going to concatenate them. So we're going to say X and S. So we're going to concatenate. Let's print and check their output. Their number of channels should be 512 plus 512, that is 1024. Height and width would remain the same. So things are fine till now. Back to slide. So now it is followed by these two yellow blocks. So this means conv block repeated 2 times. Okay, let's get back to it. Conv block, input X, number filter 512, again because it is repeating 2 times, so we also gonna write it 2 times. Okay, so this is our decoder 1. Let's print its shape at last and check if we are working fine or not. Okay, so we are working fine till now. So now we're gonna have decoder 2 like this only, just the input and some number of layer would be different. Back to slide. So now the output of this the conv block would act as input for second decoder. So first deconv layer, okay, and for our Z6 we have now this blue box is repeating 2 times. You can understand deconv, then conv layer, then again it is repeating again deconv and conv, then we concatenate. So let's follow this. So first of all, this X would be passed through deconv block X, then 256 as we have known. We're going to decrease number of filter by a factor of 2 in each decoder. We are done with this part. Now with these two blue box, first deconv conv, then deconv conv on Z6. Just remember that we're going to call it S. Instead, what we can do, we can copy it from here directly, easy. So this time it would be Z6 and 256, and again we're going to copy it, change the input to S. So this is those two blue box, and we can concatenate them now. So before concatenation, same procedure, let's print their shape. Okay, you can see 64 by 64, 64 by 64. So we're gonna let's back to slide. So we're gonna concatenate them and followed by the two con block. Simple. So we're gonna copy them from here because things are same. Why do we repeat them? So decoder 2 is also done. Now it's time for decoder 3rd. Let's go back to slide. So this is the 3rd decoder here. Again we're gonna deconv this, apply the deconv block, then this blue boxes, now these are increased by 1 more time. Okay, so this is absolutely same thing as decoder 1 or 2, just these boxes are increasing. So we're gonna say X is equals to deconv block X previous input, previous layer output. Then okay, one mistake, see, we need to decrease this 512 by 502 to 256. This is the bad thing about copying, that sometime you forget. So let's we'll do it by ourselves, but the bad thing is layers are repeating. Now let's copy it from here. So it is Z3rd now, and we need to have 128. So this would, these two layer we're going to repeat 2 times. So input would be S. I hope you get it now how this is working. So Z3rd as the input, then here S output, then SX S input for this layer, then something that goes so, and at last we get this. So now we're going to concatenate them. Again I'm copying them, but this time I would remember to change the number of filters. Okay, so like this decoder 3rd is also done. Now we're going to move on to the decoder 4th, and here we don't have any blue boxes, we just have 2 yellow boxes because height and width of this input image is same as that of this. So let's just check this. Okay, print X dot shape and Z0. Okay, so this is 128 by 128, 250. Okay, when so now this X first one would be upsampled by a factor of 2 using decon, so it would become 256. Then they both have same height and width. Let's write decoder 4. So if you see, again the output of con block would go to this decon layer, okay, with number of filters as 64. Let us copy it 64. Then now no blue boxes, if you see, just two yellow boxes, and we concatenate. So I'll copy them from here. So you're gonna say S. This time they would be Z 0, and number of filters 64. I know this is kind of don't seem right just to copy paste, but this saves your time. Okay, like if you are new and new to program, so just I would recommend don't do it. But if you are now like you have doing it for a long time, so I know, so you would understand it, you can do it. But for new guy, you need to practice it. Okay? So we have this decon, then we have this skip connection done. Now concatenate followed again by the two yellow blocks, means two cone blocks. So we're gonna copy paste it. So you would just be saying this guy just copy pasting, but like I hope you get the concept. Like if I write it every layer, so it would become long video. Only I think we are reaching near 40 minutes of video, and this is it. It's a really long video, like 40 minutes kind of documentary and my whole tutorial is more than 40 minutes. So the kind of I'm just saving times for you. So now we have this cone one by one. So this means we have reached the end of the decoder. We are on the output. So we would have an output layer. Output layer would be a one by one. So here one as number of channel would be number of output channels would be one, because I'm assuming we are working on binary segmentation. Kernel size one by one. This X would act as input for this layer, and we would build a model now using the model class we have imported at the beginning. So this model would take input, output, and we have given it a name. So this is the implementation of UNET-R in 2D. For 2D, this is the whole implementation. Now let's check if it is working by saying model.summary, and let's run it for now. Okay, what is this? Okay, just this B is removed by somehow. Okay, let's just do it again. Okay, I think everything is fine. Okay, now you can see the output layer. Let's go to the starting, see the input layer also. Okay, so this is the input layer, and we have all the intermediates layer, and finally things are working fine. So this is about the entire implementation of UNET-R for 2D. Just this is for 2D. Okay, use it for 2D task. Let's say you want to do it for multi-class. So what you would do, you would change the number of classes here. Instead of one, just write number of classes you have, and here instead of soft sigmoid, replace it with softmax. This is the change you need to do to convert it from binary to multi-class segmentation. So we have reached to the end of the video, so I would like to say thank you. If you have any more questions, you can email me, or just you can also message me on Twitter. I usually reply but late, and sometime I may not reply. I may be busy in my exams or research paper. So I'm saying I'm sorry if I do not reply. So make sure that you don't forget to like, share, and subscribe the video. Thank you. Have a nice day.